Monday is a holiday. Please don't come here, you will be lonely. Second announcement, I owe you a study guide. So by end of day, you should have a study guide up. If for some reason I get busy and that doesn't happen, somebody send me a very angry email and I'll make sure to get that to you as soon as I can. The angrier or more ChatGPT generated, the better.
I prefer the latter.
Make it both. How mean can you make ChatGPT and say, I didn't write this? All right, last time we were talking about regular grammars. We introduced this idea, which was left linear or right linear, depending on where the non-terminal is in this string. You can see that we only allow up to one non-terminal, which is what makes it a linear grammar. There's only one variable, and it's always at the end or at the beginning. So if you think of this recursively, you're coming up with the leftmost parts of the string, and then making a variable for the very end, and then coming up with the remainder of that, and then something at the very end. So it's linearly denoting the string from left to right if it's right linear, and linearly denoting it from right to left if it is left linear, because that non-terminal is on the left. So what comes later is on the left, the closer to the beginning part of the string. So that was a regular grammar. Let's give you an example. Here are some productions. Question, is this grammar left linear or right linear? First and foremost.
Left.
Left linear, that's where the non-terminal is. It's always on the left-hand side. And there are 0 or more terminals and a single non-terminal up to a single non-terminal. So this is a left linear grammar. Some possible derivations from this, strings that are in this language. You could generate something like AAB. And you see that at all points in time, the string, as we're deriving it, begins with the non-terminal. And then we are expanding our definition, incorporating more terminals as we go. So we're denoting that this string ends in AB, and then we have a non-terminal here that says there's more stuff at the beginning, but we don't know exactly what that is. We make that derivation, and then there was the old AB, but we've now derived that what comes next before that is another AB, followed by some more stuff at the beginning, and then we just go straight to B, and then straight to the lowercase a. So every time that we go through this process, we're adding to the beginning of the string until we have determined what it is. Okay. Reveals itself from right to left. And it's left linear because of the non-terminals on the left. So conclusion, because we had a path through this grammar that produced that string is a member of the language that is defined by this grammar. Another example, here are some productions. Left linear or right linear?
Neither / right.
Which one of those? You can't have both.
I'd say neither.
Neither. Yeah, that is correct, because we have a production here where the non-terminal is on the right, and a production where the non-terminal is on the left. The grammar has to be consistent with regards to where that non-terminal is placed. So this is not a linear grammar. It is a grammar, but it does not necessarily represent a regular language. So neither. Grammar is not regular. Yeah.
So for it to be left or right here, it has to be non-terminal on the left or the right for every single
production in the grammar. Yeah.
Oh, okay.
Is that the only requirement for the grammar to be regular?
It needs to be that one non-terminal, so you couldn't have something like a capital B. You can have up to one non-terminal. So either 0 or 1, and then the position of that non-terminal always has to be far right or far left.
a little bit confused. So why is, maybe I misunderstood. I thought, is it not regular because it's not left or right linear or?
Yeah, since we have, it's these two productions that. In this hand, the production, the non-terminal is on the far right. On this one, it's on the far left. It has to be consistent across the entire grammar.
Okay.
The entire grammar is left linear if the non-terminal is on the left. The entire grammar is right linear if all non-terminals appear on the far right.
Gotcha.
Since we have two different productions, one is a left linear production, one is a right linear production. The grammar isn't either left linear nor right linear.
What about S to A? Does that cause an issue? Just the fact that we have a non-terminal by itself?
That is just fine.
Okay.
So it's 0 or more terminals followed by 0 or 1 non-terminals.
For like A, instead of lambda, we have like AAB, that was the same.
Because it's just lowercase a, lowercase a, that would be fine with, as long as this didn't exist.
Okay.
Then we would start to be building a right linear grammar.
Oh, okay, I see.
And if the non-terminal is in the middle, it also invalidates the.
Right, it has to be at the far left or the far right. We cannot recurse in the middle is one way to think of that. We have to recurse from the far left of the string or the far right of the string. And every rule has to recurse on the same side of the string. Any questions? Any further questions on that? These are all really good clarification questions. All right. How could we construct a DFA or NFA out of a regular grammar? Imagine that we have a grammar and the question is now, given this grammar, could you construct an automaton? We'll start with a right linear example. So here are some productions. The process for this is that we want to start with states that represent every non-terminal. So we're going to make states that represent, in this case, variable 0 and variable 1, what I'm assuming this V stands for. And then we have a new state that we introduce called V sub F, the final state. What this first production tells us is there is an edge between V0 and V1 that consumes an A. So as we construct this, you can imagine that at the beginning of this grammar, we are at V0 and we need a definition for what does it mean to be at V0. We need some path that consumes some characters and some input in the same way that a grammar would derive that string. We need a path from this state to some final state once we've completed that derivation. So when we see something like this, this says to get from here to here, we must consume this character. So it's equivalent in a DFA of going from a state labeled the left-hand side to a state labeled the right-hand side, consuming the characters that are in between that. And you may need multiple edges to do that, since an edge can only consume a single character. And as you see in this production, you can consume two different characters to get back to this point. So you may need to add some states to this. It's gonna get in the way, isn't it? So from V sub 1, we can get back to V sub 0. We must consume both an A and a B to do it. So I'm going to add a, doesn't really matter what I call this, U midpoint. Who knows? We must consume both an A and a B in order to get back to V sub 0. From V sub 1, though, we can also consume a B and be done. There's no further variable or further definition when we reach this point. This is where we should get to our final state. So we'll make some final state V sub F, and we can transition from V sub 1 to that on a B. From here, we just have to make sure that we have a total function and add a trap state to make it a DFA. This is a perfectly legal NFA. But if we wanted to turn this into a DFA, we note that there's no A transition out of QM, there's no B transition out of V0, and there's no transition at all out of V sub F. So all of those transitions would go to trap states, or a trap state. So maybe this helps you to be able to better understand things like regular grammars or how all of these relate to each other. Any questions on that? Really rapid fire through these things, but they're not too bad. That's what I just drew. You can also imagine going from a regular expression definition and trying to come up with a regular grammar based on that expression. So here is a language that's defined as a regular expression. Imagine needing to come up with a grammar for this. Let's start with a right linear grammar. I find that right linear grammars are a little bit more intuitive. The first time you do it, where you start with what's on the left, kind of the way that you read left to right. A right linear grammar will begin with the beginning of the string and do as necessary. So things to look out for in regular expressions are repetitions. Repetitions, so star closures, are going to represent recursion in grammars. The ability to go from a non-terminal back to itself, or some non-terminal that you've seen before. And whenever you have something that is guaranteed, like this beginning AA, then you can immediately state that as a terminal. So how I read this is I'm going to start with a start non-terminal. I'm going to guarantee everything that I can guarantee at the beginning of the string. So this guarantees you an AA. And what comes after that is something, some number of B's. So I need a variable that represents some number of B's. So that is what this next non-terminal is going to represent. Whenever we have that repetition, we don't know how many times it's going to happen. So we need to further define how many times it can happen. This can happen 0 or more times. So this A should be able to produce a single B and recurse, or produce nothing. At the end of this, however, there is something else. There's a single A, and we can't produce that here. So we need the ability to then do something about that. Any thoughts on how we could handle that? Go here.
Would it be just replacing the lambda with A?
Yeah, you could basically say at the very end of this, we know this is going to terminate with a single A. So once we're done repeating B's and B's and B's and B's, we make a single A. And we have now allowed for an arbitrary number of characters of terminals, and the non-terminal, the single non-terminal, is always on the far right-hand side. So that does work. And you can always break it down linearly like this. If you didn't want to do this A right here and immediately see it, you could add another non-terminal. It says when we're done, we go to a something. Whatever it happens after this is a big question mark. And then you could further define what that is in a further scope. It just happened we could backtrack this to this point. But whenever you have more stuff, you just make another variable representing the more stuff and linearly define the more stuff. And you just have B arrow lowercase a. You would be done there, but we can backtrack that up here and it's a little bit nicer. Great. we will see that if there are, I'll kind of give this hint because there are times where you might see this in the future. There can be multidimensional repetition within these kinds of languages. So you can imagine something like this is surrounded with an additional dimension of repetition. Now we have repetition inside of repetition. When you see something like this, you need a structure that is going to look like S arrow. You're going to linearly break down what's inside of this. And that would look exactly like before. We have the A arrow, B, A, or I'm going to continue with this because it shows kind of the process, B arrow, A. But then to continue and repeat this whole process, you recurse that dimension and go back to the very start. This allows us to repeat the entirety of the logic that we've defined. As you define it linearly, when you reach the end of it, you just go back to the beginning. And if there's three-dimensional repetition within this, then you would have a three-dimensional recursive process within the grammar, etc. All right. That's basically it for regular grammars. Any questions on the concepts of regular grammars or some of the conversions that you might do between aspects of regular language we've seen so far? Yeah.
So does this language have a left linear grammar? Because
Yes.
it does?
Yeah, everything has both right linear and left linear.
But
Maybe
how?
we'll go do that. So instead of starting at the end, at the beginning, you start at the end. And so we'll say, what can we dictate from the end of this string? We know there's an A and then there is some repetition. So I'm going to put the variable up front and stop the language with that we know for sure. This A's definition now, we need to be able to add a B and recurse at the front because it's left linear now. And then when we're done with that, we would just have the AA, that's the very beginning. Or we could, again, make this our own variable and further define that down below. So it's just about kind of a placement and whether you're reading the string left to right or right to left. Nothing else about the logic of how to construct this changes at all. That's a really good point. All right, it's time. Find your preferred method of caffeine. It's time to dive into the pumping lab. Okay. First, we got to motivate this thing. I'm not going to throw something challenging at you without talking about why it's important that we need to know how to do this. So far, what we've shown is a bunch of ways to show that a language is regular. Ways we can do this? What have we talked about so far? What are the 4 ways that we can show that a language is regular?
Certain DFA.
Construct a DFA. What else? Construct an NFA. What else?
Grammar.
Construct a regular grammar. Yep. And
Regular expression.
construct a regular expression. All of those 4 do the same thing. They show that a language is regular. 1, 2, 3, 4. There's a gaping hole here. How do we show a language is not regular? That's what's going to be the big challenge. It's very easy to show that it is regular because we can construct one using the tools that allow for the construction of such a language. But to show that it's not regular, we have to say that it is impossible to do one of these things. We cannot construct a DFA. We cannot construct an NFA. We cannot construct a regular grammar, or we cannot construct a regular expression. Just because you have tried to construct a DFA and failed, it doesn't mean that one doesn't exist. It might just mean that you haven't seen it yet. So we need a process that is more complete. We talked about what a regular language is. We have a finite amount of memory. Regardless of the length of the string, the amount of memory that we need for this is embedded in the number of states in a DFA, or the number of productions in a grammar, or the size of the regular expression. But none of that is a variable that can change based on the length of the string. So I pass in a string with 100 million characters, and I still need the same number of states in a DFA to be able to say yes or no to that 100 million character string. We can't expand the DFA to get bigger if the string gets bigger. So to go into this, we're going to refresh ourselves a little bit on a concept from discrete. Who remembers the pigeonhole principle? Possibly one of us. Excellent. So the goal is we have n objects, and we want to put them into k boxes. If we have more items than boxes, then we know that there is at least one box with more than one object in it. 3 boxes, 4 objects. In order to put those 4 objects in boxes, there has to be a box with at least 2 items in it. There's no way to disperse 4 items into 3 boxes such that there are 1 or fewer objects in the box with the most stuff in it. In fact, we can say that one box contains at least the ceiling of n over k objects. Some examples. For some reason, you are a really, really festive person, and you like red, green, and blue socks, but not typical colored socks. So you stumble at night, the dryer tells you it's done, you absolutely can't see anything, and you know that you need a pair of socks for the morning, but it's pitch black. You go in, you can feel that you have socks. How many socks do you need to pull out of the dryer to guarantee that you have at least 1 pair of socks for the next day?
Nine.
Good guess. Think of it kind of in the worst case. You pull out the first sock. Does it matter what color it is?
No.
Let's say that it's red.
Okay.
You reach in, you pull out another sock. We're gonna withhold having a pair as long as possible. What's the color of this second sock? Green. Now we have a red sock and a green sock. We reach in, we pull out the next sock. What color is that sock?
Blue.
Blue. We still don't have a pair. We reach in, we pull out another sock. There's no way now to not have a pair. It either has to be red pairing with the red, green pairing with the green, blue pairing with the blue. That 4th sock is what's necessary to guarantee that we have a pair of socks. So that's kind of phrased another way, the ceiling of n over k objects. What does n have to be? What is the smallest that n could be such that n over k, the ceiling of n over k is 2? And the ceiling of 4 over 3 is the first, 4 is the smallest number that guarantees that the ceiling of n over 3 is 2. How many people do we need in a room to ensure at least 2 people have the same birth month?
13.
13 people. Again, kind of a worst case. The first person's birthday is in January. The second person's birthday is in February. Third person's is in March. With 12 people, we end up with a person with each month. As soon as we put in that 13th person, they have to pair up with someone in the room. There's no 13th month. So 13 is the maximum number of people. Minimum number of people to have 2 people with a birth month. How about at least 5 people sharing the same birth month? I have not heard the right answer yet.
Wouldn't it be like 5 times 12?
It is not.
Look at, 13, 14. Whatever.
Because. After the 12, we're not gonna fully. Why? So it's gonna be a big number. I think it's gonna be, it might be like 12
Yes.
the first time, the next time it's gonna be 11%. For the second pair, maybe that was what.
Two.
For the third pair, it's gonna be.
You said the answer is 60.
It is not
60%.
Wait.
Is the logic correct? So for the first person, it's 12, in the worst case. For the next person, it's 11 in the worst case. For the second matching birthday. Wait,
Not quite.
at least 5 should see.
Is it 49?
We finally have an answer. This is right, it is 49. Why is it 49?
Because worst case scenario, you have 12 people have different birth months, and the next 12 people are distributed over the 12 birth months. You do that 4 times now. 4 people share the 12 birth months, and then the next person you add has.
Yeah, that's exactly right. So we're going to distribute the first 12 people across all 12 birth months. Then the next 12 people over 12 birth months. And now we need one more person to guarantee that 3 people share the same birth month. So the same logic, if you think of it kind of like a table, you would have a 12 by 4 table, ensuring that we have the maximum number of people such that we don't have that 5th person who shares that birth month. We agree that with these 48 people, if we had 4 people with every single birth month, we would not have an answer to having 5 people sharing the same birth month. But that's the maximum number of people. As soon as we have one more person, the question is which birth month do they share with? And that forces the answer. It's also the minimum number of n, such that the ceiling of n over k is 5. As soon as you have 48 over 5, then the answer is still 4. But when you have 49 over 5, now the ceiling of that, 48 over 12, 49 over 12 gives you 5 for the first time. So that's how I think of it. But yes, answer is 49. 4 times 12 plus 1. All right, so now we're going to dive into this is a refresher on the pigeonhole principle, the extent to which we will need it to be able to show what we're about to show. This is going to take probably a couple days just to go through the logic of, because there's a lot of intuition to divulge here to make this easier. Rather than just throwing this at you mathematically, there's a lot of intuition behind why this works. So one of the languages we saw very early on in this class, a to the n, b to the n. Is that language regular? Could you construct a DFA to recognize a to the n, b to the n? Or an NFA? Or a regular expression? Or a regular grammar?
Yeah.
Go ahead and work on that. See if you can construct this. Yeah.
Steps get all the things feedback, so that's.
Yeah.
I see.
Yes.
No. Okay.
Oh.
But
Oh,
it's just some amount of it and some amount.
The N must be the same.
I had the same actually thought as him. I don't know why. I didn't think of them being equal.
Yeah, they need to be equal.
Impossible.
It is impossible, but I want you to go through that process of trying to make it work so that you see why you get stuck. Before I iterate, I'll draw on the board how I envision this and why it can't work.
It's because sort of we can't see the amount of B's when we're looking at the amount of A's.
Yeah, we need to pair. Once we're starting to see the B's, we need to pair them with the A's, which means we need to have counted the A's beforehand. That means we need a number of states to represent the A's. And since this is unbounded with regards to N, we can't bound the size of the DFA based on that. If this said N is less than or equal to 10, we could do it. If N is less than or equal to 1,000,000, we could do it. But because it's unbounded, we get this issue. So I'm going to start drawing what would be a solution to this if we had that condition N is less than or equal to something. So we're going to have an initial state. I'm going to call this, let's call this A0. And then I'm going to make a final state B0, saying that we've seen 0 A's. When we count them up, we need to get back to 0 B's. The difference between A's minus B's has to be 0. So I can make a lambda transition, since this is going to be an NFA, between this. This accepts the empty string, N equals 0, A to the 0, B to the 0. When we see our first A, we're going to move to the right, and that's going to make A1. We could, at this point, lambda transition saying we're done seeing A's. That's what this down transition is going to say. And then we'll go to B1, which we can go backwards to B0 on a B. And if from A1 we saw another A, we're going to move right to a place that we're going to call A2. If at this point we're done seeing A's, we lambda transition down to B2 so that we can move back this direction on a B. And this would be complete if N were less than or equal to 2. But you can see how this structure is really going to just expand forever in this dimension. We're never going to be able to handle a value of N that's larger than the number of A states that we've made. If we make more states here, we can handle A to the N, B to the N for larger N. But to be able to handle an unbounded N, this DFA needs to be infinitely large. That's NFA, since we have lambda transitions. It's basically a DFA. But that's kind of how I see why we couldn't make a finite size machine for this. As N gets larger, we need to incorporate more and more states to be able to make this work. Any questions on this construction or kind of some intuition for why this might not be regular or requiring finite amount of memory, finite numbers of states? Right. So one way to think about it, infinite number of possibilities for n. And so by the pigeonhole principle, we need at least one state where multiple values of a to the n map. This is going to create a general case for us where we're going to need to be able to use this idea moving forward. So from here, we end up proceeding with a proof by contradiction. If we remember proof by contradiction, we're going to make an assumption. That assumption is this language is regular. And if this language is regular, then a DFA with a finite number of states exists. Since the language is infinite, there must be some state somewhere in the middle of this where multiple strings meet. And we will show that a process that does this ends up creating, if such a state exists, then there are multiple paths from the beginning to the end that one of those paths creates a string that's not in the language. Since in order for that to exist, we have to have such a middle state by the pigeonhole principle. So you would assume that a DFA exists that accepts a to the n, b to the n, only if n equals m, where m here is the number of states in the DFA. We're going to start variabilizing the number of states in the DFA because no DFA exists for this. But in a proof by contradiction, we're going to say, assume a DFA does exist and that DFA has m states. Yeah, I'll describe this in a way that's easier to understand than this, at least initially. So don't worry about this for the moment. We'll come back to it. So some properties of DFAs that you'll want to take into consideration. We have a transition graph. A DFA is really just a transition graph. If there are no cycles in it, the language is finite. Why is that? So we have some DFA starting at some Q0. And maybe there are some paths out of this to some more states, but we never have any cycles. And maybe some of these states are final. Maybe this state goes here. Maybe this state is also final. But there's no cycle in this graph, right? Does it make sense then that the language that this DFA accepts is also finite? There are a finite number of strings, finite number of ways to get to final states. You can iterate this path to get to that final state. You can iterate this path to get to that final state and this path to get to that final state. This DFA accepts 3 strings. There's no other path or way to get to a final state. Convince yourself of that because it's very important. As soon as we add a single cycle, we go from a finite language to an infinite language. So just convince yourself of the minimal case for this is something like this. How many strings are accepted by this language? Yeah, an infinite number. 0 A's, 1 A, 2 A's, 3 A's, 4 A's, 5 A's, 6 A's, 7 A's, that doesn't ever end. If this weren't the case and this weren't final, and we go to another final state, we go there on something, but we go back on something else. Is that language infinite? This represents just all odd A's, 1A, 3 A's, 5 A's, 7 A's, that also never terminates. It's still infinite. So what differentiates an infinite language from a non-infinite language is just there existing a cycle in your DFA. All finite languages are regular. You just have to iterate all paths that create all of the finite strings in that language. So the only interesting languages are those that are infinite. And in order to have an infinite language, there must be at least one cycle in a state machine. So every infinite regular language has a DFA with a cycle with a non-empty edge. If there is a cycle, then that cycle can be skipped or repeated an arbitrary number of times. That's what creates the infinite strings in that language. So we could now create a variable that represents the number of times that we iterate that cycle. We are going to now break a path through this DFA into 3 components. And I'm going to draw this out as just 3 states, but it does not need to be 3 states. This could be an arbitrary number of states for any of these. So we are going to have an initial state, we're going to have a final state, and we're going to have a midpoint that is where we end a cycle. So we need to get from the beginning to a cycle. We need to iterate a cycle in some capacity. Then we have to get from that cycle to the final state. We're going to call this edge label X. We're going to call this edge label Y. And we're going to call this edge label Z. So X, Y, Z is the path from the initial state to the final state that iterates this cycle once. Does that make sense? The string X, Y, Z is in the language of this DFA. Is XZ in the language of the DFA? We take this path to here and then this path to here.
Oh,
And end up in the final state. So this iterated the cycle once. XZ is also in the language, and it did the cycle 0 times. We could also do this cycle multiple times. We could end up with X, Y, Y, Z, and that's in the language. We do the cycle twice. So we now have a way of generating an infinite number of strings in this language, and it's just based on this idea of there is a cycle. We're going to break down a path from the initial state to a final state as getting to the cycle, iterating the cycle, and getting from the end of the cycle to a final state. So this happens once, this happens an arbitrary number of times, this happens once. And you can use that to generate an infinite number of strings in the language. Questions on that intuitive idea? This is a way of thinking about acceptance. There could be multiple cycles in this, but we're going to use this generic idea to show that there exists some string. If a DFA did exist for this language that we are going to say is regular, we could find some string X, Y, 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 Z that is not in the language. In that case, we were just going to say there is such a way to break this down. If we break it down in such a way, then every single repetition of Y needs to pump, thus the pumping lemma, to be able to produce something in the language. If there exists some value of the number of Ys, the number of repetitions of the cycle that produces something that's not in the language, then this DFA can't exist. So that's where we are headed. I'll probably draw this diagram a few more times as we go through some more, but that's the basic idea. So basically all of that. So the pumping lemma. The way we're going to do this, let L be an infinite regular language. So this is kind of the language that you'll want for showing a pumping lemma. You say, let L be an infinite regular language. Then there exists some positive integer m. We're going to call m the number of states in the DFA that accepts it, such that any w that's a member of that language with length w greater than or equal to m can be decomposed as w equals xyz. The reason, how much time we have? Just enough, excellent. The reason we say we care about m is you can imagine that there are that many states in the DFA. We need to pick a string that we ensure has to have gone through a cycle. We can't have a string that goes directly, I'll draw this again, because the three-state one is a pretty good example of this. You can imagine that we have some characters that we read. If we are looking at a string of length 2, it is possible now to get from the start state to the final state without going through a cycle, as long as you pick a string that is less than the length of the number of DFAs in states in the DFA, sorry. But as soon as we allow for a string of size 3, AAA, in order for this to be accepted, we need an additional edge here. And that edge has to create a cycle. There is no additional edge we can add to this DFA of size 3 that does not create a cycle. We could add an edge from here to itself, here to itself, here to itself, here back to here back to here, or here back to here. Every single one of those completes a cycle. So the reason we say an integer m is such that the length of the string is greater than or equal to the number of states in the DFA is that it forces there to be a cycle in the recognition of that string. Does that make sense? Maybe a show of thumbs. How do we feel about that idea? For the most part, people are keeping with me. That's good. All right, so we still have that XYZ, where once we have this string that we know has to have gone through a cycle, we can then break the string down into those 3 components: getting to the cycle, iterating the cycle, and getting from the end of the cycle to the final state. That's what that X, Y, and Z represent. So now that we have quite a few symbols on the board, let's actually label them just to make sure there's the number of states in the DFA. And again, this is a proof by contradiction. No such DFA exists, but we're going to assume that one does. In that assumption, M is the number of states in that DFA. Never instantiate M. It will not help you. We're always doing this vaguely, abstractly. W is our string. The length of our string, greater than or equal to the number of states, breaks down into those 3 components. X, again, was getting to the cycle. Y is iterating the cycle. And Z is getting from the end of that cycle to the final state. All right. There are some conditions on this. We know that the length of X, Y has to be less than or equal to M. This makes sense when you think about it. Getting to the cycle and completing the cycle takes at most M characters for that same reason. If there are 3 states in the DFA, the first character gets you to the second state, the second character gets you to the last state. Once we have that third character, we have to have completed a cycle. So this says the length of getting to the cycle and completing the cycle has to be fewer than or equal to the number of characters of the states in the DFA. Once we have that third character, we've completed a cycle, which means we've gotten to a cycle and we've completed a cycle. So that is something that must be true. Expand this to 4 states. As soon as you have 4 characters, you've completed a cycle. Expand to 20 states. As soon as you've seen 20 characters, you've completed a cycle. Possibly fewer than that, but that is the cap on the number of characters you have to have read in order to complete a cycle. M-1 characters, you go through each of the M states. In the worst case, 1 more character, you complete a cycle. Last one, the length of that cycle has to consume at least 1 character. It's a good time to have a long weekend. So we'll come back to this on Tuesday and dive back into this in a way that hopefully we can get a good way into how to fully prove that a language is not regular. But this is all of the background material, a lot of the background material you need to be able to logic your way through one of these groups.
Is Monday a holiday?
Monday is a holiday.
Oh.
We have Martin Luther King Day on Monday, so don't show up.
Right. So now I thought it was a couple weeks.
And I will have a study guide to you. We will have a review session next Thursday. So you can come with questions and I will happily answer or give practice problems for whatever concepts you want Thursday, the day before the exam next month.
The two of those to this class.
Yeah, I need to keep up with that a little bit. It's been this last week that I have. It's been busy, but yeah, I need to do that. On my list for today.